Now we're on 14.5, polyprotic acid. In this section, we're going to extend previously introduced equilibrium concepts to acids and bases that may donate or accept more than one proton. So far we've really been focusing on acids that contain one ionizable hydrogen, and these are called monoprotic acids. If they have more than one ionizable hydrogen, they are polyprotic, meaning many. So polyprotic acids ionize in steps. So first there's the one ionization and then they go through another one. And when it goes through the next step, the Ka ends up getting smaller with each successive step. So the acid becomes weaker and weaker as they give up more and more hydrogens. A diprotic acid has 2 ionizable hydrogen atoms per molecule. And again, the ionization takes place in what is called stepwise ionization. So 2 steps for a diprotic. The first ionization is going to take place to a much greater extent than the second. For example, sulfuric acid is a strong acid. Its first ionization has a Ka1 of more than 10 to the second. It has complete dissociation. It is a very, very strong acid. But it makes its conjugate base of H2SO4 is HSO4 minus. So you still have a hydrogen that can be given off. So it can go through a second ionization, giving then SO4 2 minus, and this second Ka is 1.2 times 10 to the negative second, which is still fairly high compared to some of the other weak acids we've been looking at. Triprotic acids have 3 ionizable hydrogen atoms. We also can have polyprotic bases that can accept more than one proton in succession. Let's go ahead and look at an example. Carbonated water contains a palatable amount of dissolved carbon dioxide. The solution is acidic because CO2 reacts with water to form carbonic acid. And we want to know the concentrations of H3O+, HCO3-, and CO3 2- in a saturated solution of CO2 with an initial concentration of H2CO3 of 0.033 molar. So yeah, soda is actually acidic. Careful with your teeth. So looking at these Kas, you can see that Ka1 is much, much greater than Ka2. So we can treat them separately. So let's go ahead and focus on the first ionization reaction by itself. So H2CO3 plus H2O, H3O plus HCO3 minus. And let's make an ice table because we're looking at equilibriums again. No H2O. We're starting with 0.033 molar H2CO3, starting with about 0 hydronium and 0 HCO3 minus, losing some X of carbonic, gaining X hydronium and HCO minus. So equilibrium of 0.033 minus X, X, and X. So that's an awful looking X. And we can go ahead and assume that X is much, much less than 0.033. Looking at that Ka value, it's super small. So that becomes 0. Our Ka then is equal to X squared over 0.033. And we were told already what Ka is. And that's 4.3 times 10 to the negative 7. Solving for X, that gives us a concentration of 1.2 times 10 to the negative 4th power. So this now gives us our bicarbonate, which is HCO3 minus, and our H3O plus concentrations. So very similar to what we just did, the second ionization is going to be almost the same type of calculation. But let's go ahead and look at the ice table anyway. HCO3 minus plus H2O liquid gives us H3O plus CO3 2 minus. Now the amount, though, that we're going to be gaining here when we're talking about the X at equilibrium is going to be really, really small. So we have an initial concentration of bicarbonate of 1.2 times 10 to the negative 4. We just solved for that. No water. H3O, we just solved for also, and that's 1.2 times 10 to the negative 4. CO3 2 minus, 0. Now the change, again, we're losing some X, gaining some X, gaining some X. But with how small Ka2 is, both our H3O and HCO3 are way greater than it. So it's not going to change anything. So our X here is much, much less than 1.2 times 10 to the negative 4. So both of these can go to 0. So now the Ka for the second reaction is equal to 1.2 times 10 to the negative 4 times X divided by 1.2 times 10 to the negative 4. And those cancel each other out. So our Ka here is equal to our X, which is equal to 4.7 times 10 to the negative 11th power. So that is equal then to our concentration of CO3 2 minus. So to make a nice big summary here, the concentration of H2CO3 is equal to 0.033. It really isn't changing. H3O plus is equal to 1.2 times 10 to the negative 4th molar. HCO3 minus is equal to 1.2 times 10 to the negative 4th molar. And CO3 2 minus is equal to 4.7 times 10 to the negative 11th molar. Whew, that barely fit on there, but we made it work.